Our next talk is from Erik Risser, and he is a conservator here in Antiquities Conservation at the Getty Museum, and his talk is Considerations of Alternative Mount Designs for Three-Dimensional Objects. Thanks. It is here,
okay.
And then I believe, Gus, the laser pointer for this one? Is it the red button?
Yes,
it's bright. It's actually
okay.
bright up here.
That's advancing forward and back.
Yeah,
you got it. All right. I had hoped to be able to move around. I'm not somebody who usually likes to stay in one place, and particularly with the nerves I've got, typically I'll get those out by pacing a stage. So I have to be fixed here, obviously for the people online. So please bear with me. Hopefully my nerves will ebb as I get into this. But I really want to start by thanking the organizers of the International Mount Makers Forum for what has been an incredibly interesting and thought-provoking day and a half to this point. I hope to be able to contribute to that with this talk. It is going to be a little bit of a tightrope walk for me in the sense that I'm going to be talking without notes. So I'm going to be using images basically as a visual prompt to cover the salient points. But significantly, what I'm going to be talking about is actually not work of my own to the great degree. It's the work of a mount maker at the Los Angeles County Museum of Art named David Armendariz. And I'm going to be talking about his work because I'm very familiar with it. Dave worked previously here at the Getty in my department and was made a significant contribution along with B.J. Farrar and Mackenzie Lowry in the development and codification to our approach of mount making to our permanent collection, which very much still to this day informs the approaches that we take on to our changing exhibitions and to our short loan objects. So with all of that said, the reason I'm presenting this is one, because Dave would not present it himself, but two, is that I'm familiar with the methods and materials that Dave has employed in what he's presently doing at the Los Angeles County Museum of Art. But why it's interesting to me is that based on the background that we have that's shared, and that allows me to understand his mentality as, again, the techniques and the materials, it's the adaptations and the changes that he's made to those techniques in order to adapt it to the new logistical situation in which he finds himself. And that is really what I find to be very interesting, this idea of being able to take something that we know is efficacious, but then finding a way to make it efficient and fit into his newer environment. So with that said, this first slide is basically an image of one of the galleries of ancient Greek ceramics at the Louvre. And this is really meant to undermine the fact that we're talking about an object type. I'm going to be talking about a specific object type. In this sense, we're talking about ceramics. Everything I'm going to show is ancient world. That's my sweet spot. That's my interest, so please forgive me. But please understand, we're talking about an object type. So with ceramics, whether that's coil-made, whether that's wheel-thrown, what this really is meant to illustrate is the great variety in size, in shape, in weight that is possible with that, and a system that you can adapt to work with all these various sizes and shapes. So think to yesterday's talk of the British Museum, where they're talking about the stone axes, the 70 plus that they had to put on display. Again, those are of a object type, but each one of them is different in size, shape, and very individual. Yeah, please do. Sure. Hear me better now? Okay, sorry. Now I have to hear myself. That's the bad part. Okay. So in essence, we're talking about an object type. And again, a general approach that is adaptable enough to allow you to deal with the individuality of each object, but still be efficient in terms of the amount of time that it takes to do that, but significantly in the materials, the cost thereof, and in the equipment that's necessary to do that. So what he's done I find to be very applicable to a great number of scenarios. I'm sure that a lot of you find yourselves in, whether that's in private practice or in, when you're dealing with extreme time constraints or real budgetary constraints. But anyways, the idea is we're talking about an object type here. Okay, reinforcing it, I'm going to be beating you over the head with the same thing, so I apologize up front, but here is just another image, again, really underlining the fact that this object type here, talking about ceramics in a singular gallery, you have one of the largest vases from antiquity, down to a medium to small to very, very small. And again, is there an approach that allows you to deal with the great majority of these scenarios that is safe and effective and truly adaptable? Okay? Again, driving on the same point, different shapes, different sizes, but more importantly, within these, there is these inherent eccentric hollows or voids, right? Basically the cavities of the undersides of the feet, and of course, the cavities of the body themselves, and how those can be used in a practical sense in the mount making. How Dave has utilized that based on the techniques that I know from using here, but also how the adaptability that he's done has allowed me entree into adapting some of my own personal interests, which, following on from Stefan, is really about the use of magnets. And so that's what I'll get to at the end. I'm spitballing in front of all of you. So really what I'm hoping is, a lot what I'm going to talk about here, I'm sure it's not new to anyone. But many of you may have already experienced with this, and I would love to hear that. But I'm also throwing a lot of this out here as to ideas, and to a great degree, some of the experience and the experimentation that's happened to date, so that hopefully people will take this and walk away from it and make it their own. And then hopefully in 2, 4, 6, 8 years, see you back at another IMF presenting what you found. All right? So in any event, this is the what we'll call the approach that I'm familiar with, which these are 2 amphorae from on display here at the Villa. So this is part of the ancient Mediterranean collection, of which I'm part of the conservation department. And the 2 basic approaches that we've adapted, I'm sure these are well known to everyone, but I'll just simply go through them very quickly. On the right here, you're seeing a clip system. So this is basically an external form of immobilization of this object. Now, this isn't so much about we're worried about the public interacting with these pieces. These are what we're calling seismic mounts. The whole point of this, these are inside vitrines. So again, we're not worried about necessarily somebody interacting, tugging, or lifting. We're worried about the eventuality of an earthquake here in Los Angeles. So the idea of this external immobilization is really immobilizing in the lateral and in the vertical. So basically in your various forms of movement. The clips here are an external form of immobilization in association with an internal interface. So that interface effectively is cast into the cavity. It is not joined in, but is attached down to the deck. And then together with these, effectively what that does is that prevents lateral movement in it. And because this comes up and over the top here, it also prevents vertical movement, okay? This vase here, being of a very similar type, is a lot more top-heavy. You have a much heavier rim and a much heavier handle. So effectively, this is a much more top-heavy object, where if force were to come in the form of an earthquake, these may not be sufficient to restrain this, or you may have such an accumulation of force in those 3 points that it could result in damage. So in those instances, we've developed a contour here to follow the profile up in the vertical. Now, of course, this is interchangeable between clips and this. The idea is you can use 2 clips with a contour, whatever it is that the object specifically needs. But the idea here is that what this allows you to do is to have a stabilizing or bridging external element. It will bridge between a foot and a body, which are made separately and then joined, so a potential point of weakness, but significantly allows you to tie off here under the rim, at the shoulder, or potentially down here. In any or all of those is a way of effectively lowering the center of gravity. So again, as force comes in lateral, a lower center of gravity, less tipping, less force being placed in down here, and the object basically being held still, okay? This here is a detail of those. What you're seeing here, this is quite sleek, but really what you have to understand here is that you have a threaded rod. So you have a hole in your deck and you have a threaded rod that then is either drilled and tapped into the underside of this and soldered, and therefore it means that it is affixed to the underside of the deck or the display surface. Whether that means that may mean you need access to the interior of your case or access to the underside of a buildup. Here instead you have a tail or a tab, which effectively allows you to secure to the top of the display surface or deck, okay? So these are just details of those 2 basic systems. This could be for a clip if you were to limit it here, or all the way up for a contour. And of course, this works in association with the fact that you are tying off up above, typically with a monofilament. Okay, so I talked up Dave. Let me talk you through a little bit of what I've just gone through and how he's adapted that, and how I find that to be very interesting, given that he's then able to tackle many issues of object type. So whether that ceramic is ancient, whether it's a Art Deco from the earlier part of the 20th century, whether it's Mesoamerican, whether it's a Ming Dynasty vase, the concept is the same, and he can tackle that with a very simple, straightforward, and again, very efficient system. This is basically what I've seen as a change, and what I find very interesting is that he starts with basically sheet metal, right? He starts with steel, and effectively what he does is he takes the footprint of the object. Okay, again, very simple, particularly something that's wheel thrown. You don't really have to interact with the object. So as a conservator, one of the things I love about the system when I talk about the efficiency and the adaptability, the efficiency to me means less physical interaction with the object, both in terms of what it takes to gather the information and to fabricate, but significantly in the installation and in the deinstallation of the object. Okay, so he's taking the sheet steel, basically cut the footprint, and then he's cut these slots in. Now, based on the gauge or the thickness of the steel, that's directly proportional basically to the size of the object that you're going to be working on. What the adaptability here is how many clips you really need. Do you want 3? You could have 4, 5, 6, 7. So again, something very easy to decide what you need to the object and then implement. And of course, knowing the thickness, you can use simple flat stock that is of the same gauge or even a higher gauge if you want something that's slightly thinner. Now you look at this and you say, okay, what's the big deal? Well, when we're talking about an installation or a deinstallation, the big deal to me is right here. Before, whether it's 3 clips or 2 clips and a contour and an interface, you're talking about 4 holes on the top of a deck. 1 internal, 3 external. Here you're talking about a single point of connection, okay? That single point of connection, 1, means you have less coordination between points, so less probability of mistakes. But also, if you mistake drilling out here and you have to move, or let's say a curator changes their mind as to where they want something, you have a big problem in terms of patching your deck if you're drilling through. Something like this, if you're still within the footprint of the object, much easier to adjust and simply move the object. But the part that I really find very interesting about this is that he's taken the interfaces that we always used before, and now he places the interface over that steel plate. So effectively what he's doing is what was an element before to preventing lateral movement, he effectively is turning this into a washer and a nut. Okay, so these pieces no longer have to be affixed mechanically. The clips themselves, they slot in and they slot out. Okay, so by fixing through here, fixing this and this through one piece into the deck, you could fix them using a screw, a bolt, you could use wax, you could use resins, as we saw with the Harvard Museum talk yesterday. All of those are on the table. Again, that's an adaptation you can build into the system, quite simply depending on what you needed. But the reality is that this then just allows you to simply place the object and slide the clips in place. Now you have vertical restraint as well as horizontal restraint, but you've done it in a way in which is very easy to fabricate and to implement. So this is then again just laid out side by side. And when I'm talking about that idea of adaptability, here is some other objects, again, of a very small scale. Here, a Janiform Cantharos, but where you can see 4 clips have been used. And again, you have the steel plate, you have a small concave, this is mold made, small concave space underneath, where that interface does the same thing. Or here, an Ascos on the left, or a gilded Cantharos on the right. So these are all small. The intrinsic weight of the pieces allows you to get away with simply using clips, right? But as I said before, maybe that adaptability is one of those clips becomes a profile. At what point does that profile stop in the vertical? That's what I want to get to at the end of this talk, where the magnets come in, but right now we're going to look at scalability. So again, that adaptability in terms of the scale. Here, again, beating you over the head always with the same type of thing, just looking at a plate with the slots and clips, but you can tell from the interface that this is a much larger object. It's a deeper, wider interface. So this would be, tantamount to some of those we saw earlier in the talk. He did not furnish me with an image of what this looked like afterwards. But here, what I wanted to highlight was the fact that here you have a mechanical immobilization or restraint on the exterior. And what has been opted for here is to then also look at adhesive restraint and a combination thereof. And why that's interesting to me is, obviously here what you're doing is you're sharing that spread of force in the eventuality of that coming in between these three external points, and then you are sharing that with an adhesive restraint. Again, here it's simply using, I think, what is a museum wax. But the idea is how you can adapt this to adapt this. And that's really where I want to get to with the discussion of magnets. Okay? So in a similar type vase as to this, you can see traditionally this is how we've handled them. You know, we felt that in essence you are top heavy enough and you're tall enough that we need to have an external restraint that travels fairly high up the vertical of the object. These mounts are incredibly effective. They're very effective at what they do, and in these instances, they're also effective in allowing for the proper display of these objects. You can see here, they do bisect a decorative surface, but here these decorative surfaces are fairly monochromatic. This is slightly problematic, even if you faux it in, but again, for the most part, it's off to the side. Based on the casework, oftentimes you can put that in the back or put it in a discrete place, so it's not a problem. I can't necessarily say the same thing about this. This is not to criticize heavily this mount. This mount, again, is very effective at protecting this object. What it is not very effective at is not obscuring the decorative surface, which is one of the great significance of this piece, which is why it's in the round. Now, I'm not meaning to be disingenuous. Part of the reason why this is here is because this is actually a point of weakness in here. There actually is a blind crack, which is why it was felt that there needed to be this bridging element that went high up to basically unify these two through, again, taking any force and traversing it and bringing it down into the deck. My question is, using that basic technique that I've seen Dave develop, is there ways in which, again, you can adapt that so that you can necessarily maybe reduce the amount of vertical disturbance that's needed, to maybe just limit it to a number of clips, or maybe a bit pie in the sky? Could you ever make it to the point where utilizing this cavity and now maybe considering this one, could you actually get rid of all external restraint? So this is the spitball part. And this is just a little bit of a practical as to having seen this done. Here you're seeing the cavity of the underside of a foot, and here you're seeing a cavity of the interior of the body. And effectively what you're seeing, of course, as mentioned in the previous talk, magnets, they're amazing things. They are magical. It's literally in their title. But they do have limitations. And I think you could see that with some of the objects that were previously, you can go up to a certain point and then you have to stop, particularly when you're talking with a cantilever. Here, though, that's not what we're talking about. We're talking about things that are displayed in the vertical to a deck. Here we have a lot of volume. So the reality is you can do a lot of magnet stacking on the type here so that you can determine and you can dial in the pull strength that you need. But the idea is, in order for you to understand what you need in terms of the size of the magnet as well as the placements of them, of course, what is possible in terms of the cavity you have on the most limiting one, which is this one here, but also what are the forces that you're trying to do. You have to define what you're trying to do, and you have to define basically what is the weight of this object. So to say this is that sweet spot of the amount of pull force that is necessary to either, maybe I can't actually achieve what is the total weight or beyond the weight of the object, but maybe I can achieve enough of a pull force that I don't have to put a contour high up. Maybe I can limit it only to the point that it goes to between body and put a foot ring. Again, minimizing the visual disturbance, but still creating an effective mount. What I would love to see is sort of that end point, and what I will continue to try to experiment with, and what I hope other people will take and work with, just whether it's ceramic or not, the idea where you have the ability to employ internally magnets. How far we can take this. So here the idea is you have four, and the point being is that with a singular you're not going to get sufficient pull strength. Now, one of the things that was also mentioned by Stefan, of course, is the distance between magnets. The fact that here you have something in between, they are backed off of each other. There is a space in between. So you have to understand how much that affects the ideal pull force, and then significantly the density of the material that is in between. Both of those will directly impact how much pull force is actually endowed. But there clearly is a pull force in that the magnets here, this is basically an ethafoam that has been scalloped out so that it basically can take the concave form of the interior of the body, and then the magnets here placed below. So they're being held in place simply through the magnetism here. So you know there is a pull force, but how much? So here, if you say, I need to get to 40 pounds, and this one only gives me 5. Well, it's a help. Maybe I can reduce a little bit, but if I can start actually creating more or start stacking in here, can I get up to that 40? But also what you're seeing here is the fact that this one is different because these have the poles all in the positive, say, and this one in the negative. And then, of course, you have the opposite situation on the interior where you have the negatives and one positive. The reason for that, of course, is trying to, how do you implement putting in this interface? Because, of course, that pull force means that it can get out of control and you could slap it down inside. But by basically reversing a polarity, if with a slight turn you can bring things in where there still is a repulsion, you can simply rotate and then in a more controlled soft landing effectively put this where it needs to be. And likewise, through a rotational motion, you can basically find the tear strength you need to basically back the magnets off and pull it out. Okay? So this is then that translated into an interface, again with the plate below and clips, and then the interior one translated into resin as well. Again, the ethafoam still below, so you do have a soft padding between the ceramic surface and the magnets. Tyvek can be put there, Velara, any number of things. But what this has allowed in terms of that total pull strength is for an object this size and this weight basically displayed with only 3 clips. And at that point, not the need of a contour that travels up to the handle of the neck. All right, that's what I got. I can't go hide.
No, you don't get to hide. Do we have any questions? We are way over time, so I'm going to limit it to 2 questions. Sorry. You can email Erik, though. You know where to find him.
Unfortunately, yeah.
You can email Erik. Is that okay with you?
It's
sorry.
Fine. No, it's fine.
I'm sorry.
Again, I welcome comments. I would really love to hear people's experiences thinking about these things. Again, none of this, I'm sure, is revolutionary or even all that new, but I think it's worth just bringing to this forum because this is about sharing. And I really would love to hear people's experiences, and if not, if this is something that's new to somebody, and hopefully that can plant a small seed that then people can go out and make this their own. Adapt it to their own needs, and then come back and present it at the next one of these.
How are the clips secured at the bottom?
The clips are basically slid into place. So the idea, of course, is the interface being placed there and secured through that. The clips actually can't come up, right? They can only slide in line with the slot. So you have to very intentionally apply force on the line of the deck in line with that slot. And of course, if you're talking about 3, each one of those is in a 120. So the probability of that happening in a seismic event, that following exactly in line to get that to back out, is pretty minimal. It is still possible. So with that said, there's a very easy workaround. Put a tiny dab of wax at the interface between the deck and that, and at that point, the only way to fail that is very intentional force to pull it back. But again, if that's slotted correctly, it has to be very much in line with that slot. Any force that is slightly to the side basically causes it to bind. That's what I love about that system. You don't have to have 4 points of securing. Sorry, I got a little excited. Literally, all you have to do is slide them in until they're, obviously they're padded out, they're conformal, and they contact. And then to reverse, simply to slide them out. Now, it's not as simple as, whoop, again, there is a level of friction in there in that slot. Now, to be even a little sexier about it, if you really wanted to, but again, the idea was to make this really simple. If you were to take those slots and you had them T-slotted, again, that's an even greater reinforcement. Or maybe you don't have as much of a interface that you can do there. Well, then you can basically translate that same thing where you T-slot it. But the concept is still there. And for that concept, it's really what I thank Dave. That's something he really just opened my mind to something which the adaptability of that I thought was brilliant. And then it was like, well, how can you just keep working with this to then effectively try to make something that's easy to employ as well as to take away? So again, that efficiency I think is key in so many ways, but also that adaptability of it by mixing and matching and then incorporating. You really can start playing and figuring out different things. Not all of it's going to work, and it's not going to work in all scenarios, but that's not the point. It may cover quite a few. One more question, since there's only two.
Hello. I'm curious. I had this question actually for the last presenter, but I think it applies to this one as well. Mm-hmm. And it has to do with I was really interested in the system they employed to test the mounts, yep. Especially against cantilever, falling over. And so I wonder if you could comment on, testing methodology that
Sure.
maybe accompanied this.
I mean, I think as you saw in Stefan's talk, the only way of doing any type of testing is kind of real world. I don't necessarily encourage you to go out and use a real object for that. If you want to test like on a ceramic and see at what point you're going to get that failure, how much stacking you have to do, you need to have developed an idea of what's the ideal, but understand the density and the thickness in between. And that's very individual to the object. So oftentimes it really is simply a testing of trying this one, and how much pull strength it actually takes. So that's one of the things, some of the work that I'd like to do in the future with others here is that we would like to try to, as much as we can, standardize, understand standards between these types of thicknesses in these types of materials, whether those are woods, whether those are resins, whether those are different types of metals, whether those are ceramics, what that effect that has on the pull strength. Unfortunately, that isn't necessarily fully out there yet. Again, magnets are very well established for two-dimensional and lightweight three-dimensional. When we're getting into bigger and heavier, we don't really have a codified testing, so that really has to be done. So a lot of it really right now has been trial and error. I hope that answers your question. There isn't no hard and fast rule. A lot of it is seeing what works and what doesn't work. This is the weight that I have of this object. This is the force I'm anticipating. So how can I basically mitigate that? How much pull strength do I need? Well, here, again, you can do a pull test, but that's one of those where we need to sit down and say, here's all these different thicknesses and all these different materials and all these different densities, and literally do pull tests and figure out this one, which in an optimum says it's 50 pounds of pull force, but when you have this distance and this much density, it's actually 5. So if I want to achieve that, I want to achieve 40, and I only have 5, I either have to then increase the number of magnets or start magnet stacking somewhere else. That help? All right.